Okay.
All right, so welcome everybody to today's seminar, which is going to be given by Dries Vermeulen. I don't think that Dries needs much introduction, as he is a regular contributor to the field of mathematical game theory. Dries is working at the Department of Quantitative Economics at Maastricht University, so he's actually a colleague of mine. Now, maybe a few words about Dries. Going back in time, Dries did his PhD on the topic stability in non-cooperative game theory, and with an emphasis on the Koolberg-Mertens stability. He wrote his PhD thesis at the University of Nijmegen in the Netherlands. And ever since, Dries has been working on, and he is an expert in various topics in game theory and related topics. If I may say so, Dries is a very versatile researcher. And just to name a few areas that he has been working on, I went through his publications, even though I know quite many of them. Just to name a few topics: stability and solution concepts in non-cooperative games, auctions, bargaining and cooperative games, social choice, finitely additive strategies and measures in non-cooperative games, and also various papers on application areas. Today's topic will bring us back to one of the first topics that Dries has been investigating, I think, but we will see. The title is A New Characterization of Regular Equilibrium, and this is a joint work with Dieter Balkenborg from the University of Exeter. And Dries, we are very happy that you were willing to give this seminar today. We are all looking forward to it. So as you know, you have 1 hour, and then you already said so questions can come during the talk. And if there are questions, then after the 1 hour, there's time for questions and discussions as well. So Dries.
Okay, very good. Thank you, Janusz, for this wonderful introduction. Yeah, so the work that I'm going to present today is, Janusz already said that it's, you could say something that is going back to the type of research with which I started on stability of Nash equilibrium. It's not related to Koolberg-Mertens, but it's even earlier than that. So the topic that we're doing today. And in that sense, it's also, I think, together with Dieter and I think hopefully an advertisement for these older results that are really worthwhile to keep in mind. So as you can see, and also like Janusz already said, it's a joint work with Dieter Balkenborg, who is also in the audience. He is by now retired, but luckily for me, he's still willing to cooperate in doing research, which is, and this is actually one of the topics that we are currently and most recently are working on. I think I looked it up, so at least what I remember is that we had our first conversations in the Bayreuth Sync conference. That was in 2018, so that is when we started to work on this topic. And it says here in memory of Hassani, John Hassani, because regular equilibrium was one of his contributions to game theory. And like I said, one of the, I think, one of the, you could say one of the aims that we have with this paper is to you could say to revive an interest in this type of research, because we think that it is worth doing that. Okay, so let me go through the slides. I don't know how long my talk will take. Dieter gave this presentation at least on the same topic last year in the Budapest Game Theory Conference, and he I was on holiday, so I didn't see it, but he managed to tell everything in 20 minutes. But I've got 50 slides, so usually that is an indication that I need at least 1 hour. So we'll see how it goes. But please, if you got any questions, and I would rather have that you ask them during the talk than afterwards, especially if they're clarifying questions. I think it's better to do that as we go along rather than after the presentation. And I hope I can always shorten it a bit, my presentation. So in that sense, I think I can keep it within 1 hour. Okay, so the introduction, I'm going to present first the main result, which is actually very simple to state. It says that if you have an equilibrium in a normal form game, so finitely many strategies and mixed equilibria, then such an equilibrium is regular in the sense of Hassani, which I will specify later, precisely when it is what we call smooth. And smooth means that locally, if you look at the equilibrium, the graph of the equilibrium correspondence, so horizontally you have to think of all the possible games, you fix the strategies that you have, and you're varying the payoffs that players can get, then you get a space of games. And vertically you plot the strategies of the players. Then, of course, you can plot the graph of the equilibria, that for each game you plot the equilibria, you get a graph. And that graph should locally be the graph of a differentiable function. So that is what it means to be smooth. And we're going to prove that that is exactly equivalent to being regular in the sense of Hassani.
Dries, may I briefly interrupt and ask a question? So
sure.
The way you state this here, this looks like an immediate consequence of the implicit function theorem.
Yeah, we'll get back to that. So
can you
one direction, yes, the other direction, no. Right. So that is exactly one of the part in the motivation is that it's not a triviality. Okay, so
okay, so
but we'll get to that.
Okay, thanks.
But good that you ask. So Hassani regular means that, by the way, so it's also, this for us is also very much a trial in that sense that we also find it very difficult to judge, you know, how deep all this is, because we rely also partly on old results. Some things were already known, some things were known by some people, but not by the rest of the world. So it's also difficult for us to judge exactly where our contribution, our main contribution, I think, is certainly that we try to at least, give an overview of all this. And and hopefully here and there we can contribute something ourselves. But I'll get more specifically later on. So Hassani regular, that means that the determinant of, the Jacobian matrix as it was defined by Hassani, I'll give you a definition later, is not 0. So that means that in a normal, so in a modern language, that the index is not 0. Okay, so this is the statement, and we'll going to explain what was already known in the past and also where our contribution is. And in connection to that, it is on one hand dedicated to Hassani, in memory of Hassani, but I think our paper is also very much what you could call a salute to the paper in '85 by Kojima, Okada, and Shindo, because a lot of the techniques that we're going to use in our proofs are already in their paper. You have to dig very deeply to find them, but they are there, a lot of them. And we also try to make them, to simplify the proof that they have a little bit, because we have a very specific context to which we apply it, and sometimes you can do things faster than what they did. But our inspiration definitely comes from this paper, and it's also a large part of the research time that we spent was reading this paper and trying to understand it. Okay, so that is very much what we try to do as well. The paper is called Strongly Stable Equilibrium Points of N-person games in non-cooperative N-person non-cooperative games in mathematics of operations research. But I'll come back to that as well. So the outline of the talk, I'm going to give you, the central literature, which is basically 3 citations. This is an answer to the first question, right? So we're going to explain why the results are not trivial. So that's an answer. Maybe the answer to your question, Klaus, comes here. So Then we'll switch to the definitions. So I'm going to precisely specify all the notions that we need in the paper. So regular, quasi-strict, smoothness, and strong stability. Then a bit more about the central question, which is basically what I already said, so that will not take much time. And then our proof approach. But before we get to the details of that, I want to do an example that we think is very, very illuminating. So we'll go through all the details for this paper, and then we'll see where we are time-wise, and talk a bit about the details of the proofs as far as time allows us. So that's the plan. The literature, the first paper is, of course, well, this is the start, I think, of everything we do. The paper by John Hassani in 73, oddness of the number of equilibrium points, a new proof. So what he is doing is proving that, generically speaking, games only have what he called regular equilibria. He also proved that these equilibria are quasi-strict and odd in number. So if you have a generic regular game, then it has an odd number of equilibria. And well, so this is also right, the one direction of what we are doing. If you have a regular equilibrium, then it is not too difficult to see that is basically the implicit function theorem, that close to the equilibrium, the graph of the Nash equilibrium correspondence is indeed differentiable. So that is one direction of our statement. I'll give you the proof later on as well. Yeah, so this is what was done in that paper. By the way, maybe it's good to realize that checking, well, I'll talk about that later. So let's first do the literature. And then there's this paper, Kojima, Okada, and Shindo, strongly stable equilibrium points of n-person non-cooperative games. And like I said, I think this is the paper of which we think that it did not receive as much attention as it deserves. So there are lots and lots of very useful techniques in the paper, and it's a bit of a pity because, like Dieter said, the paper sometimes reads like it is they handed in the wrong draft of the paper. So there are here and there some typos, and sometimes even statements that are not entirely correct in the way they are phrased. But if you think about it, you can recover what is supposed to what it's supposed to say, and then it is correct. So and quite interesting. So in that sense, I think it's also worthwhile to yeah, you could say, recover the paper and present all the results in the correct form. So what do? They have a few characterizations of a notion that is a bit weaker than regularity. It's called strong stability. I'll give you the definition also later on. And that is their main target, to do exactly that characterization. And yeah, so well, so the regularity condition, by the way, is a system of differential equations, and they prove that the strong stability is equivalent to solving that system of differential equations. And yeah, so it's basically first order condition. And what they, so the strong stability is saying that locally the equilibrium correspondence is the graph of a continuous function and not necessarily differentiable. So basically what they're showing is that an equilibrium is strongly stable in that sense, if and only if it solves a certain system of equations, so first order conditions. We do the same or something similar, but then for smoothness and Hassani regularity rather than continuity and, you could say, Kojima regularity. Is everything clear so far?
Will you give a difference? I mean, an example showing the difference between the two notions of regularity?
Yes, I will come to that in the illustrative example. So I'll go into details in that into that as well. But I would rather do it with the example at hand. Yeah. Okay. Okay, and then the third source of information that we use is the book by Erik van Damme, Stability and Perfection of Nash Equilibria. Book is very well written, so it's very transparent and very accessible source of information. And why it is also interesting is because in Van Damme's book, he states that there is this observation in the Kojima paper that says that cross-regularity, what we call cross-regularity, that's not how they called it, but that notion plus quasi-strictness is the same as Hassani regularity. But in the Kojima paper, this is actually, it is a remark there, but it's only a remark. So there is no proof whatsoever of this statement available anywhere in the literature so far. It's not a terribly difficult thing to do, but there is something to prove still. So these kind of, details in the proofs we try to fill. So I think what we do is, well, we talked about it at length with Dieter. I think one thing that we do is to prove that every smooth equilibrium is indeed quasi-strict. I'll give you, if time permits, the proof later on. And I think our main contribution is this. So the Kojima paper for dummies, which we mainly mean ourselves, because we spent lots and lots of time to actually figure it out. So, like I said, so a lot of the time that we spent was just that. So, okay, so this is what we're going to do. The motivation. So this is the answer to the question of Klaus. Does the implicit function theorem have a converse, right? And the answer is in some sense no. So if you take this function here, y minus x to the power 2, that is a perfectly differentiable function from R2 to the real numbers. And well, the equation fxy is equal to 0 specifies a function, right? Whether you want to have x as a function of y or vice versa, both are fine. Nevertheless, if you take the derivative, so for x you get, right, so you get the 2 times y minus x times minus 1, so there's a minus 2, and here you get a plus 2. And what you can see that in any point where fxy equals 0, the derivative is 0, 0. So in that sense, the implicit function theorem does not tell you in this case that fxy is equal to 0 defines a function. So y is not necessarily a function of x, and x is not necessarily a function of y, yet both are actually true. So it's not an immediate consequence, right? So the fact that something can be deduced using the implicit function theorem does not mean that the reverse should also hold necessarily. And in that sense, I think there is something to prove. We prove an if and only if. One direction was already there, the other one is not. The same holds for the Kojima paper. One direction is fairly straightforward, the other one takes a lot of work. Okay. So we only have sufficiency here and not necessity. So that is what we need to prove. This is another one that is a bit less convincing, I think, whether if you have a continuous function, whether you always have a stable root. And of course, we all know the examples where that is not the case. So it is true that if you have a stable root, then the function needs to go from a negative to plus or the other way around, of course. But you can see that that is not a guarantee for having a stable equilibrium.
But may I briefly interrupt again?
Yeah.
Just stop me if that's too much. With small perturbations, you can get it, right? So you can go from the left picture to the right with a very small perturbation, arbitrary small.
Yeah. Yeah, so you need something here also on the derivative, right? So you can make functions and then perturb it if you only care about continuity or so, of course, and you can also perturb, you know, the function y is equal to x in such a way that you get 3 equilibria close by.
Yeah.
But you need some also some condition on the derivative of the function. But even then, these statements.
Sure. But I mean, in a sense, you know, this is why perturbation theory was developed, right?
Yes. Yeah. Yeah, so the if and only if I think is quite special, right? So
sure, yeah, but you know, in games when you do these things, you should always take into account perturbations, and you know, that's why the natural thing to apply here is the index, really.
Yeah, sure, we'll do that, but then still, so like I said, so I have I think the special feature that we have is that we have an if and only if, rather than just one direction.
Yeah.
Okay, so this is the introduction. We'll now go to the notation and the definition. So this will take a bit of time, but there is nothing new to it. So we have a set of players, finite, and each player has a finite set of pure strategies. We denote them by I1, I2 up to IKI. This is just to do justice to the Kojima paper. This is the notation that they used there. So we decided to continue that also for our own sakes, so that we can more easily relate to our own writings to that paper. So this is pure strategies. The product of these sets is called S. And we have payoff functions going from S to the real numbers, one for each player. And the pair of S together with the sequence of the vector of all payoff functions is called a game in strategic form. So nothing new here, I guess. Mixed strategies, the notation is like this. So sigma I is a mixed strategy for player I, and it's a vector of numbers sigma ik, non-negative, and summing up to 1. The notation for the strategy space, sigma I, and a vector of such mixed strategies, one for each player, is called a strategy profile, denoted by sigma over here. And the minus i's are what it usually means, namely that you leave out player I from the profiles. And of course, you can extend the payoff function to mixed strategies in the usual way. So that was nothing new, I guess. That's just to determine, to fix the notation so far. What we are going to do is keep at least the number of strategies and the number of players fixed. And we're going to look at what happens when you are going to change the utility functions, the payoff functions. And so here's a bit more notation. The carrier of a strategy are those pure strategies that receive strictly positive weight. So the sigma ik's with that are larger than 0. The carrier of a profile is the product of the carriers of the individual strategies. And pure best responses or pure best replies are defined in the usual way. Those are the strategies that maximize the payoff function over all pure strategies. And this is a notation for the product of all these best responses or best response sets. And then, of course, we have...
sorry, I mean, if I may ask again?
Yeah.
PI is the set of all pure best responses or all mixed best responses?
Pure best responses.
But then obviously you have all their convex combinations are also best responses, right? I mean, mixed best
sure, but we don't need that in the notations later on. So
okay.
I don't think we have even in the paper, certainly not in my slides, but I think even in the paper we are not we don't need notation for mixed best responses.
Mm-hmm. And the dot in I.K is just instead of a subscript, you have this dot.
Yeah, you can put it in brackets or so, but then if you put it in a subscript, that also doesn't read very well.
Yeah, exactly. Yeah, sure. Thanks.
It's like I said, it's a notation that Kojima used in the paper, so we decided to copy that. So an equilibrium is well, I'm not sure if this is a definition, but at least it's a result, right? So that an equilibrium is a strategy profile with the property that the carrier is a subset of the pure best responses. And an equilibrium is called quasi-strict if these sets happen to be identical. So there are no best responses that do not receive strictly positive weight. And yeah, so there's of course the classical theorem of Nash that says that every strategic form game, as we defined it on the previous slides, has at least one such equilibrium in mixed strategies. And what we're interested in is which ones actually survive if we are going to perturb the utilities, right? So if you change the payoffs a little bit and then see what happens with the equilibrium. Okay, so that is the beginning. We're now going to, so what the next few slides are about Hassani regularity and associated with that, what we call cross-regularity. So that is a regularity notion that was first studied in Kojima, Okada, and Shindo. And they're both, the definitions are similar. So you take a strategy profile, sigma, and you look at one profile in its carrier. So you can take, without loss of generality, 1, 1, 2, 1, 3, 1, up to n1. So you take the first strategy in the carrier. And what you're going to do is to look at the following set of identities. So if sigma is an equilibrium, then it satisfies the following equations. So the Fi1 of sigma is 1 minus the sum over all the sigma ik. So you sum up all the weights from 1 to ki. And of course, because that is 1, sigma solves this equation, but it also solves these equations, which says that you fix the I1, right? So here in the second part is the payoff that the player gets against sigma minus I if he plays I1. And of course, if it's an equilibrium, then for all the best responses other than 1, 1, you should get exactly the same payoff. So the difference between these two payoffs should be 0. So every equilibrium satisfies these equations. And you can group all these functions together in a map. So of course here it was done coordinate by coordinate, but you can, you know, put all of them together as a vector, and that vector is denoted by, well, if it's the entire strategy space, it's called F sigma, but we will also need it for sets in between the best responses and the carrier of that sigma, and then it's called FA, and A is then those strategies in the best responses that we focus on.
So this function is not defined for strategies that are not best replies, right?
Exactly.
Okay, good.
Of course, you could do that, but then it need not be a solution to that system FA is 0, right? So that's then the problem.
It would be the solution to a system of inequalities.
Yes, exactly. Okay, so that is that. We're also going to look at one map that is a little bit different from this one, which is we take these maps Fik and we multiply them with sigma ik. And this is actually what people who have seen this before will recognize as the map that Hassani originally studied, okay? But the previous one is the one that is actually studied in Kojima. So that's why it's relevant for us. Okay, so we have this map, and then of course it's even true that sigma, if sigma is an equilibrium, then it will if you plug it into this function hik, it will give you 0 regardless of whether ik is in the carrier or not, because either the probability is 0 and then this is going to be 0, or it's larger than 0 and then it's necessarily a best response. And then the difference between utilities is 0. So for the Hassani map, you really have that is any equilibrium will automatically give 0 for any ik, not just the ones in the carrier. That's the main difference here. Okay, and that is also, you can see that also in the definitions. So Hassani said that an equilibrium is regular, and we call it the Hassani regular just for to make it different from the regularity notion in Kojima et al. So if the Jacobian the determinant of this Jacobian dh sigma is non-zero, so the index should not be 0. And something similar for cross-regularity. We say that an equilibrium is cross-regular if all the Jacobian determinants of these reduced matrices, the FAs, is non-zero for any A between the carrier and the best responses of that equilibrium, and have the correct sign. That sounds a bit vague, but basically it means that they need not have the same sign, but we know how the sign should change if you go from one A to the other one. So they may alternate in the index, but you should do that in a pre-specified way, so you can keep track of how it should change.
So this is just a correction for the dimension.
Yes.
Ah, okay, thanks.
So it's not a difficult thing to keep track of, but you need to keep it in mind. Yes. Okay, so yeah, and now we are so these are actually notions that you can compute given a certain specific sigma, right? So you can write down these maps, and so this is actually something you can test if you have the equilibrium itself. So it's you could say a local condition or a point condition. The other notions that we're going to look at are local conditions, where you really need to look at the graph of the equilibrium correspondence itself. So we're going to model a space of games as a linear space, right? So you think of the set of strategies as being fixed, the pure strategies, and you vary only the payoffs for each pure strategy profile. And then for each game, so that is a vector in some R and Rn times S, you can plot all the equilibria of that game. There's at least one, we know that. So you really get you get the graph. And an equilibrium point is called strongly stable if you have two neighborhoods, so one neighborhood of the game you're looking at and a neighborhood of the strategy that you're looking at, in such a way that you could say, if you restrict the equilibrium graph to that box that you get that way, that locally it's going to really define the graph is going to define a continuous function. So there is a continuous function on the set of games such that the only equilibria that are in this local neighborhood are the ones that really have. So for each game you have exactly one equilibrium, and it's continuous. So that is strong stability, and smoothness, like I said, is just the same condition, but then not only requiring continuity, but differentiability. So that is.
May I ask this distinction between continuity and differentiability in the context where you have all semi-algebraic sets? Everything is defined by polynomial inequalities. So what is the distinction really about?
You'll see that in a moment. So also in the example, we'll have an example of both. So an equilibrium that is strongly stable but not smooth. So is that your question?
It's more about the step from continuity to differentiability, because with polynomials, that's not really a step. I mean, this is.
Yeah, it should be genetically the same, right?
Yeah, right.
Yeah.
Generically, yeah, generically everything is regular. So
one of the key point is probably that you add some corner of two. I mean,
yes, exactly.
And then
you'll see it in the example. So it's I first look at the graphs and then you can ask the questions. So
I'll be patient.
okay. Okay. So this is the smoothness, and yeah, so the central question, like I said, so every well, this is not yet the question. This is actually what is known, right? So this is the implicit function theorem. If you have a regular equilibrium, then you look at this map that we defined, and the condition of Hassani regularity actually says that the derivative of this function is, well, if you take it with respect to the strategies, is not 0. So that means that this matrix here has full rank if you fix the U and you vary the sigmas. And that means that the implicit function theorem applies in exactly the right direction. So you get that locally, you get a function, a differentiable function even, from the space of games to strategies. So this is the easy direction, and the question is, does the converse hold, right? That's the question that we're looking at here.
Sorry, if I may ask one more time. I mean, sigma, so you vary not only, you only vary the parameters of the function, not the sigmas. I mean, when you talk about smoothness.
In the smoothness, yes. So the smoothness is the domain is the space of functions,
okay,
and the strategy, the graph of the equilibrium correspondence is a function of the utilities.
Exactly. So you don't vary sigma here in order to study this. Okay, thank you.
So the sigmas are the functions of the U's. And so the ingredients that we need to prove this is, well, so one thing that we know is that if an equilibrium is Hassani regular, what we know is that if it is cross-regular and it is quasi-strict, then it is Hassani regular. This is something that is known, but it's also something that is not proved anywhere. So I think I shall say that here. So the interesting direction is to go from right to left, you could say. So if it's cross-regular and quasi-strict, then you want to prove Hassani regularity. That is a remark in the Kojima paper, and it's also a remark in Van Damme's book. But we decided to add a short proof in the paper. Yeah, so it's only a remark because this was not their main interest. They were only busy with proving that cross-regularity is identical to strong stability, and that is their main focus in that paper.
Dries, can I ask a question on the previous slide? So it's just below the theorem that Hassani regular, if and only if cross-regular and quasi-strict. So here that I'm just trying to understand it in detail. So here quasi-strictness, the usage of this quasi-strictness is to restrict the domain of the set A, right? That you defined in the cross-regularity. Or where does it fit
yeah,
in
exactly. So right. So that means that locally, all equilibria that are played with 0 probability are actually not best responses. So they will also in a neighborhood not be best responses. So the only options that you have is to use the ones that you're already currently using. And because everything is played with positive probability, you also need to use them also locally in the other equilibria, right? So the carrier doesn't change locally.
Yeah. I understand. Thanks.
Yeah, so and we have already seen that regularity implies smoothness. That is the implicit function theorem. So what we're going to do is this. We're going to prove that smoothness implies quasi-strictness, and strong stability plus quasi-strictness implies cross-regularity. I think that is our main proof strategy. The first one is, you could say, a short proof. And the second one is, well, on one hand, a short proof if you use Kojima. On the other hand, if you go into details and you want to prove it in this specific setting, you're busy for quite some time, and that's what we did. Okay. So we try to really go into all the details and see how we can adjust it to our particular setting.
So I'm confused about the last point. Isn't strongly stable the same as cross-regular, or did I misunderstand?
Yes, but the proof is easier if you use quasi-strictness, which in our case we can do.
Okay, thank you.
But you're right, yes. So what Kojima and Okada and Shindo prove is that strong stability is identical to what we call cross-regularity. Well, our definition is also a little bit different from what they have in the paper as in their main theorem. But if you go into the proof, you say that you can see that this is actually what they're using. So they're not the system of differential equations that they have is identical to the definition that we have, but also that is part of their proof. Okay, and they don't state it anywhere. So that's why I said it's actually also for us a bit difficult to exactly pin down what is worth reporting and what is not. So, but maybe this example will help us. So what we're going to do is the following: we're going to look at a 3-player game, 2 by 2 by 2. Player 1 is the row player, so he chooses between A and B. So here row A and here B. Player 2 chooses the columns A and B, and player 3 chooses the matrix. So on the left-hand side, if he chooses A, and on the right-hand side, if he chooses B. And there is a parameter in there, which is the alpha. So if you change alpha, then you see the payoffs over here when player 3 chooses B may vary. It's a one-dimensional parameter space, right? So, so you can really think of this as a line in the space of games. And the game is denoted by this G of alpha. So the best responses for player 1. Maybe I can do that on my, I'm sure my Wacom will allow me to do this. It does not allow me to write anything, I think, at the moment. Okay, so I cannot do that.
Did you try to share a whiteboard?
Yeah, that I can do, I think. So
because if you do that, that might be a possibility, I think.
Yes. But I don't see where I can do that in this one. Can I do it like this?
I think you can only by sacrificing the current PDF.
Yes, I am afraid so. Either slides or whiteboard.
Okay, that's unfortunate, but yeah. So, but I cannot find a whiteboard. That's my problem.
Dries, can you annotate on your slides? Because that doesn't require the whiteboard. If you go to the top with your mouse, you see view options. Do you see annotate?
Yeah, but usually there is the annotate, but I don't see that one here, and also don't see a whiteboard in my sharing options. So that's my problem at the moment. I've got iPad.
Either you share the screen or the whiteboard, but not, I mean, at the moment you're sharing the screen or an application, but it's when you start sharing where you see the whiteboard, not we would have to disconnect the sharing.
Shall I stop share and then see? So I can do that. No, doesn't work. So I don't get a whiteboard. So I don't know why it's refusing that to do that, but maybe if I disconnect my Wacom. These are my slides. I don't know what went wrong. Usually I can do this, but at the moment I don't seem to be able to have a whiteboard. So my apologies for that. So I can't find it. Anyway, maybe I can just explain. So it's not too difficult to see. So if player 1 chooses A here, then you can see that on the left-hand side he gets 1 and on the right-hand side he gets 0. So then the expected payoff would be Z, the probability that player 3 chooses A, and something similar he chooses B. If player 2 chooses A, then he gets 0, and if he chooses B, he gets 1. So you can see that the best responses depend on whether Z is larger or equal to 1 minus Q or vice versa. And if you do that, if you plot that, you get this. So you have to think of this as player 3 choosing on the left-hand side or on the right-hand side. So we can, the best response is either on the left-hand side or on the right-hand side. So player, here are the A's, right? A. So that is where player 1 chooses A over here. And here he chooses B, right? So B. And player 2 is choosing, what is he choosing? I think front or back, right? So player 2 has A over here, and in the back B, and B. So he chooses whether we are in the front or in the back. And the player 3 is choosing whether we are on the ground floor or on the first floor, right? So that's how you can read this diagram. And we're talking about player 1, so he chooses left or right. And if Z is larger than 1 minus Q, then he chooses left. And if Z is smaller than 1 minus Q, I think he chooses on the right-hand side. So you see, you get this kind of linear, the line here. So this is the line Z is 1 minus Q, and that's where he switches from left to right. And in between, he's indifferent. You can do something similar for player 2. It's almost the same as for player 1. In fact, originally, this is a game that was already used in the past to have an example of an equilibrium that is completely mixed and therefore quasi-strict, but not Hassani regular. What we did was just asymmetrize this example a little bit, so to make it a bit more interesting. You'll see in a moment what that does. So this is the best responses for player 2. You can see that it's almost the same. Huh? So if we would have not have the asymmetric version, then this would be the same, look the same as for player 1. But so now this line here doesn't end in this corner point here, but a little bit above it. So that is where the asymmetry comes from. And well, we're looking for equilibria. So you want to have the intersection of these best response correspondences. And if you do that, you get something that looks like this. So you can see that if this point over here, right? I hope you see what I'm indicating. That is on the intersection of exactly that line, right? So this one here. Oh, that's the wrong one. This one here and this one over here, right? And you can do that for all these lines over that you see, these 4 lines, this one, that one, that one, and that one. And that's exactly the set of intersection points of these 2 graphs. The symmetric one would have this internal diagonal ending exactly in BBA. But because we changed the numbers a little bit, it looks like this, okay? And just as a kind of look ahead, so for Klaus, so this equilibrium over here, the 0, 1 over 6, 5 over 6 is an equilibrium that's going to be strongly stable, but not regular in the Hassani sense. So it will be, the graph will be continuous, but not differentiable, right? I denote the strategies, by the way, by the first probability of each player, right? So P is a probability that player 1 chooses A, Q that player 2 chooses A, and Z that player 3 chooses A. Okay, so so far so good. Now that we add the third player.
R, sorry, I mean, why not PQR? I mean, out of curiosity.
Yeah, so that's a good question, but yeah, so we already had, I think, an R, so we had to come up with something else.
Okay.
But maybe we need to change that. So. Okay, and then, so this is the interesting part, I think. What you see here is the best response correspondence of player 3, and you can see that it is given by a hyperbola. And if the alpha is increasing, that means that B becomes a best response more often. So then this area here on top becomes larger. So that means that this curve over here moves towards BBB, and this curve over there moves to AB. And that means that these two, so there are three equilibria, and there's the AAA here, and then these two completely mixed ones. If alpha increases, then these equilibria move apart. Okay? And you see that at some point, this equilibrium is going to be exactly at that point. And that is where we will have strong stability, but not regularity. If you increase alpha further, it starts to move along this line, and then it's again regular. It's also an interesting one because if you reduce the alpha, then these two equilibria move towards each other. And at some point, they will coincide. That will not happen, by the way, when these two, so it's a bit, so at some point, these two curves here will have form a square, right? So that is when the hyperbola is degenerate. Then these two equilibria are still apart. But what happens if you decrease the alpha further is that now the hyperbolas will be on the other two quadrants, okay? And then there's only one branch is going to make the two equilibria. And when that one is tangent to that line, then the equilibrium disappears. And that is exactly a point that is not stable, it's not even strongly stable. And then this G alpha will be exactly the direction in which the equilibrium disappears. So you could say all possibilities are here in this one example. Okay. Am I making sense for everybody? So the equilibrium you can compute, it's over here. So this is 9 divided by 20 plus or minus this square root over here. You can see the 9 divided by 20 is exactly a bit less than a half. So that's why I said that comes from the asymmetry. So it's not exactly at the half, but it's a bit more asymmetric when the equilibrium vanishes after we have P is equal to a half. And yeah, so the negative root converges to this equilibrium over here for alpha is 5. So that is the strongly stable one that is not Hassani regular. If alpha is larger than 5, then these are the equilibria and they're all Hassani stable. That's on the horizontal line. It's Hassani regular. And if alpha is exactly 119 divided by 121, that is when the square root is 0, both equilibria coincide, and then it is this equilibrium. So that is an equilibrium that is not Hassani stable. And you can see that actually there is a direction in which the equilibrium disappears. So it gets destroyed. The difficult part is always to find such a direction. So if you have that the equilibrium is not regular, then you need to find a direction in which the equilibrium gets destroyed. And that is always the difficult part.
Is it clear that it should be a linear direction, or couldn't it be some curve that is not even?
Yeah, so so that is actually what a large part of the Kojima paper is about, to find such a direction. And you can what the proof is really brilliant. So it's really very clever construction. So they use a certain type of you could say polybimatrix games where we all play bilateral games, and they use those kind of perturbations to find a direction in which the equilibrium gets destroyed.
I don't think it gets destroyed. I think it's showing that we have one direction, whereas you have index +1, one you have index -1. At the center, it cannot
right. Yeah. But that is true in the proof detail. But then the conclusion is that that cannot happen because it cannot change its sign, right? So
yes, but the contradiction is not showing that there's no equilibrium nearby. It's showing that there's a contradiction with respect to index here.
Sure. Yeah. But the consequence of that is that there should be such a direction, right, in which it gets destroyed.
Not sure.
It's a bit Tomato,
you're
tomato, I
saying
would
that
say.
the
But,
index is 0 of this equilibrium or what?
so they prove two things. Well, maybe I should go through the slides further down. So
Sure,
they
go
prove
ahead.
two things. On one hand, the index of the equilibrium cannot change. And on the other hand, there is a direction in which it changes. That's what they prove. And the conclusion then is that cannot be. Okay. So in that sense, they do prove indirectly that there is a direction in which it gets destroyed. So they do not. Yeah, I'm not sure whether the direction that they do construct has that feature. I would say yes.
So it's a
cannot,
0. Yeah. If there is a direction.
Exactly.
Yeah.
So
No, but the equilibrium could have index 0, I mean, existing, and then if you move it, decomposes into two equilibria.
exactly. The proof is exactly about a 0 index equilibria. So that's where the difficulty is. If the equilibrium itself is already plus or minus, then you don't have a problem. But the problem is with 0 degree. Sorry, 0 index.
Contradiction arises because it isn't 0 at the origin. At the equilibrium, consider the index is not 0. Because otherwise it could just jump from +1 to 0 to -1, but that's not happening.
Right. Yeah, so they prove they cannot exist. Yes. Right. So it's not about regular equilibrium, right? So we're looking at equilibria that are strongly stable. So am I saying this correctly? Now I think I do. So the proof is about strongly stable and quasi-strict equilibria. And you want to show that they are cross-regular or regular if you wish. So that's what the proof is about. So you have strong stability plus quasi-strictness, and that's what you, so it could still have potentially 0 index. But you prove that that cannot happen. So that's the proof. And that's the difficult direction, right? So you start with an equilibrium that is strongly stable and quasi-strict, and you prove that the index cannot be 0. How do you do that? You assume that it is 0, and you derive a contradiction. Okay, but let me continue. Basically what they do is well, so one thing that you can do is to look at these matrices and transform them. What happens here is that you take, instead of looking at the original payoffs, you look at the payoffs UIA minus UIB, and then B gives you always 0. Okay, so there's a transformation of the game. And of course, the equilibrium set doesn't change. And also, very importantly, the Hassani, so the determinant of the Hassani map doesn't change. So regular equilibria stay regular equilibria. And for that transformation, you can compute the payoffs if you play A, and that is in some sense all you need. So that is also already in the Kojima paper that you can do this kind of reduction of the original map. It's actually quite useful for us in this case because originally you would have a 6x6 matrix if you write down the Hassani map, but 3x3 suffices. So that's what we're doing here. So you get this map. And if this one has a non-zero index, so if the determinant of this matrix is non-zero, then you have a Hassani regular equilibrium. So you can compute this determinant. It's like this, right? Because of the zeros on the diagonal, it's easy to compute. And you see that the equilibrium is non-regular precisely when this part here is non-zero. Alpha cannot be -1 because already at the alpha is 119 divided by 121. There are no equilibria anymore. So alpha is -1.
Yeah, sorry about the transformation means this is something that leaves the best responses unchanged, but sets one set of payoffs to 0. Is that what I understood?
Yeah.
Okay, good, fine, thanks.
So and then the next step is that then you only need to look at those payoffs for A, and you can leave out the payoffs for B. So for the regularity, that doesn't matter. So this is a transformation that Kojima also uses at some point in their proof. It's one of the first steps they make, to look at this matrix rather than the original one.
Yeah, it's completely standard. I mean, it's, yeah.
Yes. Okay, so you can plug in the numbers. So this was the equilibrium, and you see that if you plug in Q is 13 divided by 24, you get 13 divided by 2, and here 9 divided by 2 is right. So that is exactly 22 divided by 2, and that is 11. So you get that this equilibrium has a 0 determinant. So it's not Hassani regular, and even it will not be strongly stable. So that is what. Because this is a quasi-strict equilibrium, that means there's only one A to test, and that is the A that is equal to the carrier, which is what we just did. Okay, so the Kojima result also immediately gives you that this equilibrium cannot be strongly stable.
So, but if I understand the example correctly, I mean, you have these curves and then you move them together. I mean, then the hyperbolas become a cross, and then the equilibria are still there. And at some point, these two equilibria merge.
Yes.
That can only mean that they have, at this point where they merge, the one has +1 and the other one has -1 index, and they merge and become an equilibrium of.
Yeah, yeah. I wish I wish that I could draw the graph, because it's really so you have this cross, right, where the so currently here and here you have the hyperbola.
Yes.
And then at the half, this will actually be the you could say the right, yeah. And then you take the other two.
Yes.
But because this diagonal over here, so this big black diagonal, right?
Yeah, yeah. So, it still crosses intersects the two now vertical parts. I mean, vertical planes.
This one.
Yeah, yeah.
So it is a little bit. It's not exactly through this midpoint.
Exactly. And, no, that's fine. Exactly. But then the two equilibria merge to a single one, and then they disappear.
Exactly.
But the merged one is actually of index 0. I mean, that's just I mean, it must be, because it's.
Yes, that's what we just. Yes, exactly. That's what we just saw. Yes.
Exactly. Okay. Good.
And that does mean that it's right. That is not Hassani regular, but it even means that it's not strongly stable. That's what I'm saying. So the second part is something that you can get from Kojima, right?
Yes. Thank you. Yeah.
So in some sense, what I'm trying to say here is that there are two ways that something cannot be Hassani stable. Either it is not Hassani regular. It's either not strongly stable, or it is strongly stable, but it is an equilibrium of this type here, right? Where simply the graph is not differentiable. So there are, you could say, two different ways in which an equilibrium can fail to be Hassani regular. Okay, I'm running out of time, I see. So where am I now? So yeah, so I also did the calculations for the other equilibrium. So this one is, I think, just standard. So this is all Hassani regular. But this equilibrium here, that's the one on the corner. So that one has a determinant that is non-zero, right? So you get -45 if you plug in the values. So that means that you cannot deduce anything yet, but you can also compute. So you know that it's not Hassani regular because it's not quasi-strict. There is a best response that is played with 0 probability, because it's a limit of the completely mixed ones. But it might be strongly stable, and it actually is. And you can check that by looking at the part of the graph that where P is equal to 0, and look at the other matrix, which is this one, and that one has a positive sign, which is exactly what should happen, right? So the sign should flip, and you see that happening in this example. So that means that this one is strongly stable. Okay. While both determinants are non-zero, right? That can happen. Okay, yeah, I am over my time. So what should we do? Maybe I'm looking now at the organizer. So basically what I'm going to do in the remainder is talk about the implication from smooth to quasi-strict, and the implication from strongly stable and quasi-strict to Crossregular. Should I do one of the two, or should I stop? What is your advice?
It also depends how long they are.
The first one is, I think, 3 minutes, so that's not long. The other one takes a bit more time. So this one is actually quite straightforward.
Sure. Okay.
So the quasi-strictness is actually quite simple. So you start with a smooth equilibrium. Our original proof was longer, but we shorten it until it's really almost straightforward. So you start with a smooth equilibrium that is not quasi-strict. Then you look at the best reply that is not in the support of sigma, right? There should be one, so we call it IKI. And you're going to look at the following family of games. So you keep basically everything the same, except the payoff for the IKI, to which you add T. So basically it means that everything stays the same unless player I plays KI. In that case, he gets his original payoff plus an extra bonus of the euros, right? That's how you can read this. And well, if the equilibrium is smooth, that means that the composite map, so you take the equilibrium sigma IT and you compose it with UIT, so that this is a differentiable function, right? So you can, for every T, you can do this. And if the graph is smooth, then this is a continuous, or even a differentiable function. So you can take the derivatives. That's what we're going to do. And we observe that if T is negative or zero, then the equilibrium doesn't change, because we had an equilibrium, so we only put weight on best responses. And the only thing that happens now is that one of the ones that you're not using gives you less payoff. So that's not going to be a best response. So at least in that direction, nothing changes, which means that in the derivatives of this composite function, you only need to look at the derivative of UIT itself, which is 0 for all strategies that is not IKI, and it is 1 for the ones where it is. And that means that for T larger than 0, at least for small t larger than 0, actually KI is going to be a strictly better response than the ones you're using in the equilibrium, right? Because this one increases linear in T, and the other ones have, well, are at best quadratic in their increase in utility. So at some point for small t, IKI is the only best response, and you're not playing it. So that is, at least you play also the ones that are not longer best response. Maybe that's, you could put positive weight on the new best response, but because of the continuity, you should also still put positive weights on the ones that are no longer best response, and that can't happen, right? So that's the proof. Then this proof, which is in some sense an adjustment of the proof that is in some sense already in Kojima, so we're relying heavily on the techniques that they're using there. And yeah, so it has several steps. Because of the quasi-strictness, you can assume that the equilibrium is completely mixed, because like Janus already said earlier, locally, these are the only strategies that matter, right? The ones that you're using in the, that you're playing with positive weight. We can assume, like in the trick we did before, so this standard trick that all the utilities of the last strategy are 0. And that means that you can simplify the Kojima maps even further. So this is the one that you're actually looking at in the proof. And yeah, so here it is, right? So now you assume, so the assumption is that you have a strongly stable equilibrium that is quasi-strict, and you assume that its index is 0, and then you derive a contradiction. Step 1 is showing that locally this map GV is a homeomorphism. That is something that is already in Kojima. So we copy their proof. And here you use a strong stability of the equilibrium. In step 2, we are proving that that locally, if the index is non-zero, that is always the same sign. Okay, so it can be positive when it's positive or non, then it's non-negative everywhere, or it is negative and then it's non-positive everywhere, either 0 or negative. That's formulated here. And this is still, you could say, a general proof. Of course, you need to go through the steps, but it is something that is not relying on the specific context that we are in. It uses Sartre's theorem and the homotopy theorem and step 1 that we talked about earlier. So in that sense, this part is still general. But the last part, so that is what Dieter said. So the last part is showing that there is a direction in which you can move, right? And if you move in if you start in equilibrium, you move in the positive direction, then the index is plus, and in the other direction it's minus. And that's of course a contradiction with what we concluded in step 2. And in this part of the proof, this is where you really use the setting. So the fact that we are looking at equilibria of finite strategic form games. And that is very specific, and also the construction is very, very specific and very clever. So. Do you agree, Dieter? Or I think this is basically what it is, right? Yeah, I think this is more or less where I should stop. I think this is also the end of my slides. So are there any remaining questions?
Yes, but I think we should first thank you. I mean,
yes,
I don't know.
That's what I wanted to jump in, Dries. That's first, we should thank you for the very interesting talk. And then, as you can see, it inspired discussions and questions quite a bit today. So let's thank Dries first of all for the interesting talk. And then indeed, if there are questions, then this is the time. Bernard, I saw you raising.
I mean, yeah. So so my question is, in computation of equilibria, there is a notion of non-degeneracy. So my question is there a good definition of non-degeneracy? Because every specific game that you have is not generic. Typically, your examples have small integers, whatever. I mean, in particular, when you want to compute something, you want to have a good definition to say this specific game. It's not generic, but it's not degenerate. So in two-player games, there's a very good definition which says every mixed strategy has never more best responses than the size of its support. So if you mix 3 strategies, you never have 4 best responses. That doesn't work in, or maybe it does work, but I don't think this is a good definition. This implies automatically quasi-strictness of any equilibrium. But in 3-player games, you can easily have a completely regular equilibrium where somebody plays a pure strategy and the other 2 people mix 2 strategies, for example. So I mean, they clearly don't have equal supports in their equilibrium.
Yeah, that's actually the example that we already had, right? So
for example, I mean, no, but so what is a good definition? And it should be done not in terms of the equilibria, but in terms of the best response correspondences.
But I think, I think I understand. If I understand the question correctly, Bernard, then I think the answer my answer would be that it really depends on what you want to compute. I think that. So you see the level of genericity that you need may vary depending on whether you look at Hassani regular or Crossregularity or right.
Yeah,
so,
but I mean, so I assume no, what I'm assuming is, I mean, you can probably write down a polynomial that must not be 0, and that's your definition of
yes.
But it might be way too strong. So for instance, if you look at the identity matrix for two-player games, I mean, that is highly non-degenerate because of all these, highly, I mean, non-generic because of all the zeros in there, but all the equilibria are perfectly regular in there. So what would be good is a good definition of non-degeneracy
I think our result shows that the original notion of Hassani was not that bad after all, right? So
perhaps yeah, okay. So
because you might think that there are.
I mean, no, here's the problem. The problem is that this applies to the equilibria. And once you have the equilibrium, I don't need to worry about this anymore.
Yeah. So
I mean,
okay,
so I want
see.
to have something that starts before, for instance, the Lemke-Hausen algorithm.
Yes, I see what you're saying.
Might not. So that, but only that. As I say, the definition in two-player games is completely undisputed and very easy. But I don't have a good one for more than two players.
Yes.
I wondered whether, yeah.
Yeah, it's a projection problem, right?
To some extent, yeah. I mean, for instance, your diagonal, the first best response correspondent of player one in your example was clearly bad because it had this diagonal going through. I mean, that was something that looked, I mean, as a possible example for degeneracy. Yeah. I mean, something that goes through a corner and hyperbola that goes through a corner is not a good idea. Anyhow, thank you. Sure. I'm still struggling with that definition.
Okay. Yeah. So yeah, we'll. Yeah, like I said, I think it's in more player games. So with 3 or more player games, this might actually be a difficult thing because so the condition is on the equilibrium indeed. So in the product space, and basically what you're asking is for which games do we have problems up here, right? And so in that sense, it's projecting semi-algebraic sets, and that in general might be a difficult thing to do. Maybe a question from me to the audience is, what do you think of this? So, like I said, so we were busy with it a lot, and I think our own interpretation of our contribution was varying from well, it's actually quite a lot to should we publish this? Am I saying this correctly, Dieter? Or
yeah, I think our contribution was always small, but
yeah, so
we always felt both the problem that actually the paper by Kojima and Chindo and Okada isn't always quite correct, and therefore very, very difficult to read.
Yes.
So getting through there was, I think, a contribution.
Yeah.
Hopefully, and for me, it's still. I understood Klaus' comment in the beginning. Well, that's all trivial, but that assumes that implicit functions theorem would be an if and only if condition, which it isn't. So, and if you look into it, there's a lot of explicit construction and usage of index theory in quite a clever way. So, if I can convince people that this is not trivial, I think then I would have achieved something.
Okay.
Just to correct Dieter, I didn't want to imply that this is trivial. I was just asking which aspect you want to emphasize here and what you're going after. So since Dries asked, what is this paper, or where should you publish this paper? It's a theory paper in the end that deals with relatively subtle differences between solution concepts that matter for non-generic games. This is interesting to a certain extent, but on the other hand, I also think that in the end, what you should care is about generic games. However, I do not think that the notion of generic normal form games is a good notion, right? You should actually look at generic extensive form games, and that's a linear subspace. Therefore, itself in normal form space, non-generic, right? Because in the end, what do we use a game for? We use a game to explain certain phenomena that we see in the data or in the real world or in lab experiments or whatever. And these phenomena we cannot see if they are not stable, statistically speaking, right? If they vary with very, very small changes of the environment, we wouldn't see them, right? So these things have to be, in a sense, robust.
Yeah, but from a stability point of view, even strong stability is still, it's one of the stronger notions of stability that we actually have, right? So
no, but what I'm talking about is how to perturb the games properly, right? So I think the normal form space is a bit too big in a sense, right?
Yes.
Too high-dimensional. The right perturbations would be extensive form space. So fix a tree or the extensive form with its information sets and so on, and vary the payoffs to the place. Right? That would be an interesting space to look at. And if we have results on that space for generic games in this space, I think these results are really useful. Right? In normal form space, I'm not so sure.
I think it's always a special case. normal form games you can always think of as a special case of extensive form games.
Yes,
That
but
I
for instance,
don't
when you look at
agree
Zenton's horse, I mean,
with.
that's a 2 by 2
sort
by
of
2
very
game.
trivial extensive form games because basically players choose at the root all the strategies, right? But we ignore all these pair of ties that come in from non-trivial extensive forms.
Did you say, Bernard?
So
Sorry.
Zenton's horse, for example, is a game which has only 2 actions per player, and it already has lots of degeneracies. I mean, and so maybe it's worth looking at some variations of that if we want to pick up Clausen's suggestion. Maybe you can have a game of that sort. Yeah. By the way, I've written, I mean, I'm writing a program now that solves these 2 by 2 by 2 games graphically and produces exactly these cubes and so on.
Okay.
Because even Zenton's horse, you have no program that outputs all the equilibrium of Zenton's horse. It's amazing. I mean, so we at least we have solved that problem. The 2 by 2 by 2 3-player game, which doesn't sound great, but it's actually quite useful. So you might
Okay.
I'll keep you posted.
Yeah. What's the language in the?
No, it's I mean it's
it's a tool. Okay, good.
No, we produce, I mean, for instance, XFIG files that display these cubes and so on. So I mean, it's yeah.
Can it handle parameterized games or?
No,
Not yet.
But we could probably make, why not? I mean, let me try to add that to the as a feature. Yeah, I took lots of screenshots here now.
Okay, good. Okay, yeah. Are there any other remarks or questions?
I have one.
Okay. Yeah.
Just a quick one, that whenever someone does research in a topic, there are always new questions arising. So what would you think that, what would be a challenging next step, or what? Ooh. It's okay, then forget about my questions.
In this context, I don't know, do you know anything, Dieter, that springs to mind? Yeah, so the question that we
Klaus
just
had a perfectly
yes.
good example. If you think, as I suggested, that normal form games can be considered as very specific extensive form games, we have a definition of regularity in these games, and how do these results now, can they be meaningfully extended to more general classes of extensive form games? And you have an interesting one.
Okay.
Yeah, the other direction I think would be computational aspects, right? So
Yeah,
I think so. I wanted to ask something about that, but Bernard asked it much more precisely and much better. So that's yeah. Yeah. Thank you.
okay.
No more questions. Thank you.
Yeah, thanks. It was very good to give a presentation. Thanks for listening, and yeah. Hopefully we can go back to also seeing each other in real life again at some point.
Slowly, I think so.
Yes.
Yes, it is.